Hello and welcome to this episode of Math with Martinez. In today's video, we are going to be looking at the graphs of rational functions. Not only that, we are also going to be looking to be able to do a little bit more than just look at their graphs. We are also going to determine the asymptotic restrictions on the domain of our rational functions and represent the domain and range like you're going to see in these next few examples on the pages to come. So let's go ahead and begin. We are beginning our discussion on rational functions, not to be confused with reciprocal functions, although they look kind of the same. A reciprocal function is going to have in the numerator just a number, and in your denominator, x, let me point it out to you, x minus or plus a value, and then something added on the end. This is the format of a reciprocal function. But for a rational function, you're going to have a whole polynomial in the numerator and a polynomial in your denominator, but we cannot let our denominator, or q of x, equal to 0. This is, in fact, a function p. We're going to call the function in the numerator p of x, and the function in your denominator is your q of x function. So let's talk about graphing these functions. Step number 1 is going to be to simplify the function. And then step number 2 is going to be to find the intercepts by setting our numerator equal to 0. That is to set your p of x function equal to 0. Then we're going to find the vertical asymptote by setting your denominator equal to 0. That is your q of x equal to 0. Then you're going to find the horizontal asymptote using these rules that we're going to list out below. Now, in order to understand these rules, we need to remember what is meant by the degree. The degree of a polynomial is the highest power of the variable in your expression. So if you have a higher power for p, which is in the numerator, than you do in the degree of your denominator, this is going to indicate that there is no horizontal asymptote. No horizontal asymptote. However, if the degree of p is less than the degree of q, then this is going to indicate that we will have a horizontal asymptote. It's going to be the x-axis. Or we could write that as y equals 0. That would be the equation of that line where our asymptote would be. If, however, the degree of your numerator's polynomial p and the degree of your denominator's polynomial are in fact the same, then we're going to have a really unique asymptote. It is going to be as follows. Y equals the leading coefficient of p of x divided by the leading coefficient of q of x. And then, once we've got all of that, we need to see, are there any holes in our function? So that begs the question, what exactly are the holes of a function? A hole is going to be the point at which there is a break in the graph. A hole occurs when there is a common factor between the numerator and your denominator. So to find the x coordinate, you're going to set that common factor equal to 0. And to find the y coordinate, you'll just simply substitute that x in and go from there. So we are going to do one example here together so that you can see how we find all these key features, including domain and range, for our rational function. Let's go ahead and begin. First step is to simplify your function. We want to simplify that function, meaning is there any factoring that we can do in the numerator or in the denominator? Yes, we are factoring like we did with quadratics. So it still is a really important ability for us to be able to do that. And no, we actually don't have any factoring that we can do because this is linear. This is also linear, so it cannot be factored. Let's just make a little note to ourselves that neither the p of x nor q of x can be factored. Okay, so step number 1 is done. Step number 2, we find the x-intercept by setting the numerator equal to 0. Okay, let's do that. Let's find our x-intercept. Let's find our x-intercept. We set our p of x equal to 0. Our p of x is that numerator x minus 4. Setting that equal to 0, well, that's pretty quick there. We find that it is just at 4. So our x-intercept is going to be when we have an x value of 4, and that, of course, means that our y value is 0. I'm going to plot that point now. Right there. Next step is to find our vertical asymptote by setting our denominator equal to 0. Let's find our vertical asymptote, which I'm going to abbreviate VA. All right, so we're going to set our Q of x equal to 0. That is, I'm setting x plus 4 equal to 0. And solving, I find it to be x equals -4 for my vertical asymptote. It is the equation of that line. So -4. At -4 on my x-axis, I'm going to have this vertical asymptote. Okay, then we are ready to move on and find our horizontal asymptote using the rules. We need to know about the degree of both the numerator and our denominator. So let's think about that together. Let's think about our horizontal asymptote. Let me try that again. Okay. So we need to know what is the degree of p of x. What's the degree of p of x, ladies and gentlemen? What is the degree of p of x? Looking at your numerator, the degree there, that is a linear function, so its degree is 1. Similarly, what is the degree of q of x? What is the degree for q of x? It is the same. It is 1. So this is where the degree of p of x and q of x are equal to each other. So we need to look at that leading coefficient of p and of q. What number is in front of each of these first terms? They both are 1. So when you go ahead and set that up, that horizontal asymptote is 1 over 1, which simplifies to just 1. We've got our horizontal asymptote here at 1. Do we have any holes? Is there a common factor in our numerator and our denominator? No, there isn't. They are not the same, and we couldn't factor it any further. So there is no hole for this graph. Now our domain we can tell by looking at our vertical asymptote. Remember that? It's just going to be all those values except -4. And looking at our horizontal asymptote can help us with finding our range. It's all those y values as long as we do not allow it to be 1, because that's where our asymptote is located. Then, ladies and gentlemen, we just use our handy-dandy graphing calculator to help us get some nice, pretty points that we can plot and connect. So I'm noticing here, I've got this point at 1, 2, 3, 4, 5. It's all the way up at 1, 2, 3, 4, 5, 6, 7, 8, 9. At -5, 9, I've got a point there. And then I also have a point here at -6. 1, 2, 3, 4, 5, 6. It's at a height of 5. -6, 5. We've got a nice point there. And then I also have at -1, 2, 3, 4, 5, 6, 7, 8. It is at a height of 1, 2, 3. At -8, it is at a height of 3. So I've got these points from looking at my table. That allows me to sketch my graph. And then on the other side, I've got some nice points as well. We've already got our x-intercept. My y-intercept is going to be right here. That's at 0, -1. I've got a point here at -2. It's down at -3. And at -3, it's at a height of -7. 1, 2, 3, -3, -7. So those points allow me to kind of get the nice sketch of this function. There you have it. That is graphing a rational function. There's a little bit more to it than graphing a reciprocal function, but a lot of it does feel quite similar now that we have a better understanding of like vertical and horizontal asymptotes. We can apply that to this type of function as well. Ladies and gentlemen, that's all for this video. If you had any questions, would you please take a moment to share those now? And until next time, stay fired up.